Hello students, good morning. My name is Dr. Mallikarjun, working with Institute of Aeronautical Engineering in the Department of Information Technology in the series of video lectures of course Operating System. Today we are going to discuss round robin scheduling algorithm. Round robin scheduling algorithm is completely preemptive scheduling algorithm. See, non-preemptive scheduling algorithms are first come, first serve scheduling algorithm. Shortest job first is a non-preemptive scheduling algorithms. And preemptive algorithms or round robin scheduling algorithm is the best example for preemptive scheduling algorithm. Shortest remaining time first is also the example also is a preemptive scheduling round robin scheduling algorithm. Round robin scheduling is a CPU scheduling algorithm that allocates a CPU time to each process in a circular queue, ensuring fair access and preventing a starvation. Starvation is a situation the process executing a long time. We will give the time quantum. We will give the time quantum means a time slice. The process can switch to another process can then execution. That is called round robin scheduling algorithm. Each process given a fixed time slice. The time slice is a quantum time. So we given the time quantum for each process that executes some time, then it gives the next process for the execution. That is called time quantum. And if it does not complete within that time, it's moved to back of the queue. Round robin scheduling algorithm is the best example for preemptive scheduling algorithm. Let's see preemptive and non-preemptive. Preemptive means that the process once submit to CPU and execute some time, then it gives to another process. Means that it's interrupt or preempt and give to other process. So it is typically based on priority and time sharing policies. Mainly, a process is switched from running state to ready state. This is the preemptive scheduling algorithm. The best example for preemptive scheduling algorithm I mentioned here, it is a round robin scheduling algorithm. See, non-preemptive means that it is a process executing until completion of their burst time. Means that the process keeps on executing, then completing their execution, then give to the next process for the executing. It is a process holds CPU till that process get terminated and give the next process, next chance to next process to the execution. So it's a non-preemptive scheduling algorithm is the best example for first come, first serve scheduling is the best example for non-preemptive scheduling algorithm. Let's see this round robin scheduling algorithm. There is a time quantum. It's a very important. The problem already given in the time quantum. So we take the time quantum and start the execution of the problem. In an operating system, a time quantum is also known as a time slice. Is a fixed amount of time that a process is allowed to run before being preempted or interrupted and placed back in the ready queue. The time quantum is for one problem you take the different time quantum, for another problem you take the different time quantum. Let's see that how to execute a problem in the time quantum. Let's see one example how round robin scheduling algorithm works. Students, see the problem. In this problem, there are 6 processes: P1, P2, P3, P4, P5, P6 process. Their arrival times are 0, 1, 2, 3, 4, 5. The arrival times. Their bus times are 4, 5, 2, 1, 6, 3. Now, in the problem given, time quantum or time slice is at 2 units of time. So, it is completely said that it is a preemptive scheduling. It is a preemptive scheduling. Preemptive means the process executes certain time and switch then to give the next process for the execution. This is a preemptive. So what is the preemptive time? Is that 2 units of time only. The process execute 2 units of time, it can switch to next process, then executing. So any process could not execute more than 2 units of time. That is a preemption. So round robin scheduling algorithm is completely preemptive scheduling algorithm. Let me take in this data structure, we use the data structure in the round robin scheduling algorithm is a queue data structure. So there is a queue in this data structure. So, and I'm taking one Gantt chart and one queue. So this is a Gantt chart. So I'm taking here two things, two data structures. One is a Gantt chart, another one is a queue data structure. In the Gantt chart, so in the 0th interval of time, in the Gantt chart, first P1 comes. So that also enter into the queue, P1 data structure. Once P1 also enter into the queue, then it's a time quantum is 2 units of time they execute. Once 2 units of time they execute, then so in the queue P2 enters, in the arrival time P2 1, that is also enter into the queue, and arrival time 2 units P3 also enter into the queue. So P1 executed 2 units of time. So P1 again enter into the queue. They're completing their executing time. P1 again enter into the queue. So P1 completed here. P1 completed. And here bus time 2 units. That is also completed. And 2 units are left. In the under 4 units, 2 units completed, 2 units left. Now P2 got the chance executing in the CPU. So P2 come into the in the CPU and executing 1 unit of time, they're executing, and 3 units of time, P2 completed their execution. Executing P2. So P2 burst time is 5 units of time. So P2 executing. So the remaining time is 3 units left. 3 units of time is left. So on up to 3 units of time, 2 units of time. So P3, P4 also, P2 completed 2 units of time. Then burst time remaining left 3 units of time. Now up to P2 as time quantum is 2 units. So P2 has 4 units of time it completed. 4 units. Up to 4 units. P4 also enter into the arrival time 4. P4 and P5 also enter into the. So P2 2 units executed, remaining left 3 units of time. So again P2 also P5 arrival time P5. Then P2 also enter. P3 enter into the CPU their execution time. So Gantt chart means which process enter into the CPU, that is decided by the Gantt chart. Which process comes to the CPU, that can be noticed in the Gantt chart. So P3 comes and their burst time is 2 units of time. So 6 units of time up to P3 comes and executing 6. So P3 2 units of time are executed 0. Up to 6 units of time, P6 also enter into the queue. P6. So P3 completed. This is 6. So P3 completed. P3 completely completed, not again enter into the queue. P3 closed. P1 So 2 units of time. So P1 comes again and executed 2 units of time. 2 units of time. So 8. So P1 completed 0. Totally completed P1. Then P4. So 1 unit of time, that is 9. So that also becomes 0. That also becomes 0. P4 also completed 0. Next, P4 also over. Next, P5 enter and execute 2 units of time. 9, 11. So 11. So no process are again entered into the queue. But again P4 enter into the queue. P5 again P5 enter it. So P5 2 units completed. The remaining burst time is 4 units of time. So the next process, P2 enter into the CPU. P2 enter into CPU. Then their executing time 3 units are left. 2 units are executing. So 2, 13. 13. Remaining 1 unit of time is left. P2. So again P2 enter into the. So now P2 here completed. Next P6 enter into the queue and execute 2 units of time. So 13, 15. So 2 units completed. 1 is left. So again P6 enter into the queue. So P6 completed here. Now P5 is there. P5 enter into the queue, enter into the CPU and execute 2 units. 17. So 2 units completed here. P5, 2 is left. Again P5 enter into the queue. Now P2 is there. Again P2 comes and execute 1 unit of time. 18. 18. So P2 becomes 0. So P2 completed here. Then P6 enter and execute 1 unit of time, that is 19. So P6 completed. Then P5 enter and execute 2 units of time, that is 21. So P5 also becomes 0. So all are become 0. So P5 also completed. So this also becomes 0. So all are completed at 21 units of time. At 21 units of time, all processes are completed. Now we calculate the completion time. Then we calculate the completion time. Completion time. So P1, check the P1 where it completed in the Gantt chart is coming to back to front. So P1 completed at 8 unit of time. That is the completion time for P1. P2 where it completed coming back to front 18 at 18 units of time. P2 completed. So their completion time P2 is 18. P3 where it is completed coming to back to front. P3 where it completed at 6 units of time. P3 completed 6 units of time. P4 completed where it's completed P4 coming to back to end. P4 completed at 9 units of time. P4 is 9. P5 where it completed coming to back to end. P5 completed at 21 units of time. That is the notice that their completed time is 20 minutes of time. P5. P6 completed where it completed 19 units of time. P6 is completed. So we computed completion time for all 6 processes. Completion time. Now we calculate the turnaround time. Turnaround time is completion time minus arrival time. That is a turnaround time. So 18 minus 0, 8 minus 0, 8, 18 minus 1, 17, 6 minus 2, 4, 9 minus 3, 6, 21 minus 4, 17, 19 minus 5, 19 minus 5, 14. 14. Now we calculate turnaround time. Then we calculate the turnaround time. Then we calculate the waiting time is turnaround time minus burst time. 8 minus 4, 4. 17 minus 5, 12. 4 minus 2, 2. 6 minus 1, 5. 17 minus 6, 11. 14 minus 3. Average waiting time is equal to, so total process 4 plus 12 plus 2 plus 5 plus 11 plus 11 by total 6 process. So that is 16, 18, 18 plus 5, 23, 23 plus 22, 23 plus 22, 5, 45, 45 by 6. That is equal to 7, 7 6 are 42, 3, 6 5 is 3, 7.5 their average waiting time. 7.5 their average waiting time. We worked out this problem if time quantum is 2. Okay, we worked out the same problem if time quantum is 4. Let me work out the same problem. Let me check if time quantum is 4. Okay, the same problem if time quantum is 2, we worked out. The same problem we worked out if time quantum is 4. Let me take data structure Q as one data structure Q, and data structure is a Q, and Gantt chart. At the 0th arrival time, process P1 enter into the queue, enter into the Gantt chart, and their executing time quantum is 4 units of time. Now time quantum is 4 units of time. P1 completely executed 0. So time quantum 4. What are the process are enter into the queue? So P1 comes and complete their execution completed. Then 4 units of time. What are the processor arrived? P2, P3, P4, P5, all are arrived in the queue. So P1 completed the execution. Again, P1 could not enter into the queue. It's completed. Then P2 comes into the CPU. So enter into the Gantt chart P2. So their execution time, their burst time, it is not completion time, their burst time. Their burst time is P2 burst time is 4 units of time. So 4, 4, 8. So here 5, 4 completed. So 1 units of time is left. 1 units of time is left. Up to 8. So P6 also enter into the queue. P6 also enter into the queue. So P2 is 1 units of time is left. So P2 completed here and again enter into the queue because 1 units of time is left. P2 again enter into the queue. Now again next process P3 enter into the Gantt chart P3. Their execute time is 2 units of time, that is 10. So P3 completed their execution completed. P3. So P3 again not entered the queue, it is become 0. Now P4 is there, that is entered into the CPU and execute. Their burst time is 1 unit only, that is 11. So P4 is also completed here executing. So it become also 0. P4 also completed. Next P5 enter into the queue, enter into the CPU and executed 4 units of time because it is 6, burst time is 6. So it become 4, it become 15 units of time. P5 completed. So 4 is completed here. Their left is 2 units of time is left. So P5 is completed here, again entered into the queue because P5 2 units of time is left. Next P6 entered into the queue and executed. P5 is 15 units of time. So P5 completed 15 units of time. So P6 entered into the CPU and executed 3 units of time. So 18 units of time. P6 completed. So it become P6 become 0. P6 completed. So now P2 is there. P2 comes and starts the execution. So P2, so 18 plus 1, P2, 1 is left, that is 19 units of time. P2 completed. So P2 becomes 0. So P2 completed 0. Next, one process P5 is only left, that comes and CPU and execute. So 19, 21 at P5 is also completed. P5, 21, that is also completed. So these are the process which completed that at time quantum 4. Time quantum 4, these are the process. Then we calculate the completion time. So coming to back to front, where P1 is completed, that 4 units of time, P1 is completed. P2 completed, where P2 completed 19 units of time, P2 completed. P3 completed, where P3 is completed 10 units of time, P3 completed. P4 completed 11 units of time, P4 completed. P5 completed at 15 units of time, P5 completed. P6 completed at 18 units of time, P6 completed. Then we calculate the turnaround time. Turnaround time is completion time minus arrival time. That is 4, that is 18, that is 8, that is 8, 11 minus 3, 8, 15 minus 4, 11, 18 minus 6, 12, turnaround time. Then we calculate the waiting time. Waiting time is turnaround time minus burst time. Waiting time. So 4 minus 4, 0, 18 minus 5, 13, 8 minus 2, 6, 8 minus 1, 7, 11 minus 6, 11, 12 minus 3, 9. So then we calculate the average waiting time. So 0 plus 13 plus 6 plus 7 plus 5 plus 9 by total number of process 6. That is equal to 19, 26, 26 plus 5, 31, 31 plus 9, 40 by 6. So 40 by 6, 6 point, so 40 by 6, 6.6 something. So in this previous problem, if time quantum is 2, we got the average waiting time 7.5. The same problem we executed in the time quantum 4, we got the average waiting time 6.6. If time quantum increases, we reduce the average waiting time. So waiting time is reduced when increase the time quantum. So that's why round robin scheduling is the best scheduling algorithm compared to all first come first serve and shortest job first. So round robin scheduling algorithm works under the preemptive scheduling process, preemptive scheduling procedure. So round robin scheduling algorithm works under the preemptive mode. So these are common. Arrival time is the process enter into the ready queue. Burst time is the process need to execute on the CPU. Completion time is when a process finishes its execution. Waiting time is the time a process spends waiting in the ready queue. Turnaround time, the total time from arrival to completion. These are common for all scheduling algorithms. But round robin scheduling algorithm has a different. It have separate feature. It is a efficient scheduling algorithm compared to all scheduling algorithms. We worked out this problem under time quantum is 2 units of time, under time quantum is 4 units of time. When time quantum increases, it reduces the waiting time that we seen in this example. Okay, students, I collected this information in the book of Abraham Silbert, Scratch, Peter B. Galvin, George Gange book, Operating System Principles. This is the title of the book. Publisher, Wiley Student Edition, Publisher, 8th edition, 2010. And also another book, William Stallings, book title is Operating System Internals and Design Principles, Publisher, Pearson Education, 6th edition, 2002. In the video, we learned how round robin scheduling algorithm works, and what under the problem example we worked out the problem under time quantum is 2 units of time and time quantum is 4 units of time. When time quantum is increases, reduces the average waiting time. This is a special feature of the round robin scheduling algorithms. Okay, students, thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.